Okay, so the last thing that we covered last time was Indianism, and we got to this slide. So it was a good point to stop from that perspective, and to pivot and shift gears to give you an example of memory to register uh, operations, which in the architecture that we are discussing is a RISC architecture with only a load store interface between the register file and the memory. So the only way that we can get to memory is through the register file by loading items from memory into the register file. And then when we want to put something in memory, we store from the register file to the memory. So one such instruction of that group is the LDUR, which means load on scale offset to register. Okay. So this operation has 3 operands, and we're going to see later that it uses the immediate instruction format when we actually see all the different formats. The first operand is the destination. So in this case, that's the register where the item from memory is going to end up. The second operand is another register that holds a we can call it a started address. In the way that the compiler may use it, this may get used as a base address, and then is going to have a sign immediate field, which we can interpret as a displacement from that address, because we'll see how we actually get to the address. And this is going to be when we discuss addressing modes, we're going to see that this is going to be a relative addressing mode. So that is the format of the instruction. So we can look at a couple of examples. The first one, if we have let's say a C expression, G is equal to H plus a member of an array that has been previously declared. So we want the 5th member of the array. So arrays in C start at 0. So this would be the 5th one. And if we further assume that the compiler made associations of G with register 20 and H with register 21, and we're going to use register 10 as a temporary, we can also assume that A is going to be an array of memory elements, and A is a pointer. So A is the address of the first element in the array, or A of 0, that would be the address. So that would be an example where we could use this instruction to code or use the LDUR instruction to bring in that array member. Another example is if we wanted to make the array number 12 equals to H plus the number A member of the array. If we have some associations, again, we can have a register that holds that pointer, and then we use the displacement to get to the right member in the array. Okay, so let's work through that first example. So here, to execute or to compile that expression, G is equal to H plus A of 4, first we need to bring that member of the array. So we said that the base address of the array was in register 22, and then we could say displaced by 4. So we're going to see that that's wrong. And if you recall, it is because the addresses are in bytes. And if we assume that this array is of integers, this may not be the correct displacement. You have to multiply by the number of bytes in the data type that you have declared that array to be. So if we assume that integers take 4 bytes, these are 32-bit integers or 64-bit integers that take 8 bytes, we will have to multiply. Now usually this number of bytes are powers of 2, and the multiplication is easy because we just have to shift. So that is not going to work. We have to do some work on that displacement given the data type so we get to the right element. So that brings us to here where we discuss that memory organization a little bit more. So let's say that this column here, if we are talking about 64-bit integers, each of these rows is one element of the array. This is element 0. This is element 1 because it's a 64-bit integer. And this is element 2 and so forth. But from a memory perspective, the memory looks like a continuous data structure that is numbered by bytes. So this is byte 0 all the way to byte 7. This is byte 8 all the way to byte 15. So bytes 0 through 7 represent the first element of the array, element 0. Bytes 8 through 15 would represent the second element of the array, or element 1. So what that means is that this displacement needs to be the actual byte address. So we have to multiply by the number of bytes in the data type that the array is holding. Okay? So if we want the fourth element, what we really want is this one here, the fifth. So this is element 0, element 1, element 2, element 3, and element 4. So you see that we will have to multiply the displacement, because what we want is the actual address or the actual displacement in bytes, 32. We will have to multiply 4 times 8, which is the number of bytes in the data type that the array consists of, which is 64-bit integers, which are for 8 bytes. So that would be the correct displacement. So register 22, the base register or the base address, is this address over here. Let's say that it was 0, but it could be anything. And the displacement is always going to be 32. So if this holds the initial address of the array, the way that the load is going to work to figure out the actual address where it needs to load the item from is going to add the contents of register 22 with the constant 32, and that's going to be the actual address. And then is going to load, because this load is going to load 8 bytes at a time, is going to load those 8 bytes into register X9. Remember that registers are 64-bit registers. So we get the right item into the register. And then we can do the addition. We can do the addition, okay? And then we can use the store that works exactly the same way, but instead of getting the data from memory to a register, gets the contents of a register into a memory location, but the mechanism to find out what is the actual address is the same. So if we're going to put some result, and you understand now how we get to the A of 8, if we're going to store this result in A of 12, we would have to multiply 12 times 8. And that would be the actual displacement that we would put in the displacement field. So again, for the store, storing the contents of a register, which is this one, this operand here, into an address is going to be the contents of another register, a base address, plus an immediate field, which can represent a displacement. This field is signed, so that allows you to move up or down from a base address in memory. So this displacement in the case of 12 would be 12 times 8, or 96. So this is the whole example here. So here we are loading A of 8. In this case, 8 times 8 is 64. That's the displacement. Register 22 will have the address of the beginning of the array, or A of 0. We add those two, and the actual A bytes starting at that address are going to go into register 9. Then if we assume that register 21 has the value of H, we do the addition and put the result in register 9. Notice that the destination can be one of the sources. So in essence, we are overwriting register 9 with the sum, which originally had A of 8, but that's okay because we don't care about this value anymore. We just want the sum of these two items. And now we can store that sum into A of 12, which is the same base address of the array, but now with a displacement of 96, which is 12 times 8. And we have done then the operation. So why do we want an architecture that relies for most operations on register accesses? And as I mentioned in the previous presentation, that's because registers are much faster than memory. And the main reason for that is a smaller data structure. In this case, we're talking about 32 registers, while memory is going to be much larger. It is that physical size. In the physical implementation at the circuit level of these data structures in hardware that makes the register much faster. So that's why we want to have most operations rely on register access, but we need to get to memory eventually, because the reason that registers are fast is because we don't have a lot of them. The data structure, the hardware is small. So it's not going to be enough to hold everything that we need. So we need to have an access in and out of memory. And that, in this type of architecture, the RISC architecture is going to be the set of loads and store instructions. Overall, this is going to require more instructions to be executed. But the fact that this simplicity allows you to build a faster processor turns out to be a good investment, given that overall the cost of memory, the cost of program size, because you require more instructions, is going to be less expensive. So a big part of smart compilers or optimizing compilers is going through your high-level code and trying to optimize the usage of the registers in the register file in such a way that minimizes the memory accesses. So trying to leave in the register file the variables and associate variables that are used the most with registers and leave it there as long as possible, and leave the less often used data in memory and bring it as needed. So there are a number of algorithms in compiler design on how to do that utilizing graphic theory. So now let's take a closer look at the immediate operands, because we already saw how we use that in the context of the load and store, but we can also have arithmetic instructions that use that same immediate instruction format. For example, we can have an add immediate that takes 3 operands, and we can have a source register and an immediate field and have the results put into another destination register. Again, in this type of instructions, the destination and the source can be the same. It gets overridden. So in this case, the contents of register 22 is going to be replaced with the original content plus the number 4. Why do we want immediate instructions? Well, one reason is to, when we initialize variables, that's one way of initializing a variable. That immediate constant field is embedded in the instruction itself. Now, as we'll see, since the instruction has to have other fields, we cannot have the full length of the instruction to encode this constant. So they're going to be, the range is going to be restricted, but it so happens that a lot of the constants that are used are small. So it works out. It's a common case. And remember that one of the principles that we looked at in the first chapter is to make the common case fast, to be able to enhance the performance of our processor. So that's another way of utilizing that immediate field, is with arithmetic instructions or immediate arithmetic instructions. So let's take a look back at a refresher of binary numbers real quick. So if you recall from 312, the range of a binary pattern of n bits is going to range from 0 to 2 to the n minus 1 if you are looking at it as an unsigned number. So this would be a few examples. And you recall how to convert from binary to our actual decimal number, essentially multiplying each of the bits by its weighted power of 2, where the weight or power starts with 0 for the least significant bit on the right, and then 2, 4, 8, or those are the actual values, but the actual exponents are 0, 1, 2, and 3 in this case. So the exponent is the bit position started on the right with the least significant bit with an exponent or a weight of 0. So this would be the power of 2 here would be 1, 2 to the 0. Here would be 2, 2 to the 1. Here would be 4, 2 square. And here would be 8, 2 to the third power. So you can always convert to our usual decimal number. So this would be for unsigned integers. So that gives us some range, some common ranges. So if we're using 4 bits, we know that we have 0 to 15. So that's for a hexadecimal digit. For 8 bits, we have a range of 0 to 255. And 32 bits, you can see the number there, about 4.3 million. Or 4.3 billion, actually. So that works for unsigned integers. But we also wanted to show a refresher on signed integers. In that case, the most significant bit is the signed bit. And there are different ways of encoding the assigned bit, assigned integer, meaning that the number can also be negative. So the range is not just 0 through some integer, positive integer. The range also includes some negative numbers. So you could have sign magnitude where the most significant bit is the sign and 0 is a positive number and 1 could be a negative number. We could do 1's complement. So if you recall, 1's complement is when we invert every bit. Or we could have 2's complement, which is actually what we use. And there is a good reason for that, is because the other encoding may have 2 representations for 0, which is inconsistent. But for 2's complement, that's not the case. So mathematically, is friendlier than some of the other formats. Not that they could not be used with the appropriate, taking the appropriate care in hardware when you design the actual ALU, but 2's complement is what we normally use. And there are other formats. You can have some excess based formats and other base of 2 type formats. So let's look at the sign magnitude, okay? So this would be the leftmost bit is the sign bit, 0 is positive, 1 is negative, and the remaining is essentially the magnitude as a unsigned integer or an unsigned binary pattern. So these are some exercises, okay, that you can do when you get the slides. These are some examples of the 1's complement, which is essentially just inverting every bit in the pattern. And when you go to these exercises after you get the slides, which I truly recommend, you see that the inconsistencies of the 0 will be apparent and will show up. So this is the 2's complement, and essentially what we do is we take the 1's complement and we add 1 to it. Okay. Now the nice thing that this format has is not only that the zeros are consistent, but also when you add a negative number to a positive number, you are effectively doing subtraction. So you use addition to do subtraction, which is nice because from a hardware perspective, all that we can do truly is addition. And that is because the exclusive OR that you're familiar with is a natural binary adder. The logic for the exclusive OR represents the addition of one bit when you take into account 2's complement encoding. So that's what we use 2's complement to represent the negative and positive numbers. And there are a couple of slides here about excess and things like that. So I'm going just to go through that. So here are some representations for 4-bit integers in different formats. So what I want to highlight here is the 2's complement. You only have one 0, which is 0. With the other ones, you may end up with a +0 or a -0. Okay? Like sign magnitude and 1's complement. So the representation mathematically of 2's complement sign integers is the same as the unsigned. You have the value of the bit times 2 raised to the power of the bit position, starting with the least significant bit on the right. So the bit position starting at 0 go all the way to n-1 for an n-bit number. The only difference between 2's complement and unsigned numbers is that this exponent, 2 to the n-1, we're raising 2 to the bit position, which is n-1, that weight is negative. That weight is negative. So if the bit is 0, then that makes it a positive number because this term becomes 0. But if the bit is 1, which is the sign bit, then this larger or largest of all the exponents in the pattern is negative and takes effect, and that makes the sum overall negative. That also gives you the range of the largest negative number that you can have. That is when this bit is 1 and all the other bits are 0. So 1 and all the other bits 0 gives you the largest negative number, which is -2 to the n-1. And the largest positive number is when this bit is 0 and all the other bits are 1. And that would be 2 to the n-1 minus 1. So in this case, if you look at this here, all these bits are 1. That would be the sum. And if you carry that out, you would get the number -4. Because this is a large negative number. This -1 times 2 to the 31 is a very large negative number. And then you start adding all the other bits here, and you really get to a value that is close to 0. And essentially you can get any negative number in this range from -2 to the n-1 to 0. So this would be the range for 32 bits. So you shouldn't be surprised that the range is about half, not quite, but about half of what it would be if you were looking at unsigned numbers. So why do we care about number of bits? So this is an anecdote. When YouTube started, they had the counter for views on videos, they had it as 32-bit integers. And when Gangnam Style came out, it actually broke the counter because the number of views were so many that the 32 bits could not hold the number of views. And that's why YouTube changed to 64-bit integers to hold the number of views counter for videos. So that's just some interesting trivia there. All right. So to recap, for 32-bit numbers, 2's complement, the most significant bit, and in any number of bits in that matter, the most significant bit is going to be the sign bit, okay, which is going to be 1 for negative numbers and 0 for non-negative numbers. And here we have some good 0 is always going to be the old 0 pattern, and it's going to be unique. -1 is always going to be the old 1 pattern, and is unique. And the most negative, again, is where you have the most significant bit 1 and the rest 0. And the most positive is when you have the most significant bit 0 and the rest of the bits 1. If you want to negate and convert a number, what you have to do is take the 2's complement of that number. Okay? So, and that is done by taking the 1's complement, which is changing every 1 to a 0 and every 0 to a 1, and then adding 1. And then you get the 2's complement number. So this should be all just a review from 312. So I'm going pretty fast because of that. The other nice thing about 2's complement is that you can convert a number that takes fewer bits to a number that is represented with more bits by just extending the sign if you're talking about signed integers. So if we wanted to extend a byte to 16 bits, and this is what we have originally. We have just this byte here, which is the number 2, and we wanted to extend that to 16 bits. All we have to do is copy the most significant bit over. And if we apply our sum to this new pattern, we'll see that we still have 2. In the same way, if we have -2 represented as this 8-bit pattern here, this byte, and we wanted to represent it now instead of with a byte as 2 bytes or 16 bits, all we have to do to extend the sign is to copy that most significant bit, the sign bit, all the way and fill the upper byte with that bit. And if you do the sum in the new 16-bit pattern, you'll see that you still get -2. So this would be -2 in a byte. This would be -2 in 16 bits. So we have the hardware. The ISA has instructions to take care of that, because remember that we can get to a byte in memory. The memory is byte addressable, but the register is 64 bits. So if we wanted to load a register with a value that is held in a single byte, we have an instruction like load a register with sign extension versus loading a register without doing any sign extension. How does the compiler know whether to use this instruction and extend the sign or use this one and not extend it? Well, that depends on your declaration. If you declared your byte as an unsigned short integer, which in C that's what a byte is, then it would use this instruction. But if you declare in C your byte as a signed short integer, it will use this instruction. So that's why in strongly typed languages like C, variable declarations are so important, and they are in fact a must. Now, when we talk about holding numbers in a finite storage, like a register or a memory location, we have to consider the possibility that when we have the result of an operation, the result may not be able to be held in the storage that we have dedicated to it. So we can have hardware to do the operations, and this is just logic. It doesn't know. So we have to add hardware to detect whether the result can be held in the storage that we have allocated to it. When that happens, we call that condition an overflow condition. And what it means is that the result cannot be held in the value or the storage, the number of bits that we have associated with it. So if we had 4-bit registers, if we do this operation and we are holding signed numbers in this 4-bit register, which will have a range of -8 to 7 or +7. If we do this operation, we get 6. We can hold 6. If we do 4 + 4, we will have an overflow because we cannot hold the number 8. Our maximum positive number for a 4-bit register is 7. If we have 2 - 7, so that would be -5, we can hold that. 4 - 4 is 0, that's fine. And then -8, which is a valid number, and -4, which is another valid number in the range for 4-bit registers, would give us -12. That would produce an overflow because the largest negative number that we can have is -8. So we'll see that in the next chapter, when we talk about arithmetic design, we're going to see how our implementation of the ALU detects things like overflow. So let's go back and keep talking about the representation of instructions. So by now, you should understand that the ISA that we are architecting or going through the architecture of are 32-bit instruction words, and there's going to be a number of different formats. You already have seen 2 formats: the register to register, where the 3 operands are 3 registers, 2 sources, 1 destination, and you have seen the immediate format, where we have 1 destination register or a source register, another register, and an immediate format. Keeping the number of formats as regular as possible and as few as possible simplifies the important step of instruction decoding that can take some time once the instruction is fetched from memory. So we want to keep that regularity as much as possible, but at the same time we want some flexibility, uh, some girth and some power to our instruction set. So it's not like we can only have one. Although in the lab that is coming to you later on, not today, but later on in the course, you'll get to design a simple processor with a single instruction format. We're going to see that we're going to be using a lot of hexadecimal numbers. So just recall the hexadecimal digits. So this is all review. So I'm going to go through that real quick. And here it is. The main three instruction formats for the ISA that we are going to be discussing. And you can see they are 32 bits and they are divided in fields. Okay? These are the R-type instructions. Like when we add 2 registers and put the result in a destination register. So these are the fields: source, destination. Since this is used by arithmetic instructions, we can also indicate a shift amount of the main source register before it gets operated on by whatever operation the opcode encodes, and then put into the destination register. Notice that each field for the register is 5 bits. That's because we have 32 registers, and we need 5 bits to specify any of those 32 registers uniquely. So that is the R-type. You have seen that. The other one that you have seen is the I-type, the immediate type, where we have an opcode, an immediate field, a destination or source register, and the other register, which in the load and store would be the base register that we mentioned. And then the new one here is the D-type. Okay? The D-type has the opcode, has an address, has a 2-bit auxiliary operation, and it has 2 registers. So we're going to see that this format, we're going to use it later in the branch instruction. This is also a derivative of the I-type. So actually, this is the one used in the load and store, while the I is using the arithmetic immediate instructions, like add immediate and subtract immediate. Add and subtract, we use the R format, and the load and store, we use this. So this would be the immediate format, actually, not this one. Sorry about that. It would be this one, but they're very similar in the sense that they have 2 registers, 1 immediate field. This one, the opcode is smaller. That's to make that immediate field a little bit larger for those constants, because the I-type is using arithmetic, while this one is not. And then this one also has that auxiliary operator. So we'll take a closer look later, but so far we have seen all these 3 instruction formats. So let's take a close look to each one of them. So this would be the instruction fields for an R-type And let's look at an example. In this case, we're adding register 21 and register 20 and putting the result in register 9. This is the destination field, RN and RM. This happens to be the opcode, the actual opcode, and that's decided, that is specified, the actual opcode for add. This would be 21 because we are talking about register 21. We are not specifying any shifting in this instruction, so that's 0. This would be RN, which is 20, so this is the number 20. And then finally, this is the destination, register 9, so that would be a 9. So if you converted this to binary, that would be the actual machine code for this instruction. That would be what would be in memory, in program memory, to execute that instruction. That would be what the processor fetches when it goes and gets instruction from instruction memory. That binary pattern. And this would be in hex, the representation. Now let's look at the D format, which is the what is used for the loads and stores. So we have the base register at N. We have the address and the destination, or the source if we are talking about a store. It's the destination for the load, is a source for the store. And here's what we have, so to have some flexibility. We're deviating a little bit from the regularity, but this type of instruction and this format is necessary to be able to get data in and out of the register file and in and out of memory. But we do want to keep them as simple as possible, which this instruction set does. So let's look at an example. We are loading register 9 with the contents of register 10 plus a displacement of 80.
Professor,
Yes.
you have 5 minutes until 1:30.
Okay, great. Thank you so much.
You're welcome.
All right, so we're loading the contents of register 9, or loading register 9 with the contents of memory location given by the contents of register 10 plus 80. This would be the opcode for LDUR. That's the immediate address, that field, 80. No secondary operation. This would be Rn, which is 10, and then Rt, which is 9. And we would end up with this hex pattern. Finally, an example of the I format, where we have 2 registers, destination, a source, and an immediate format. And we can have an example of add immediate. So we're going to add the constant 8 to the contents of register 10 and put the result in register 9. This is RD, the destination, RN, the source register, and the immediate field. This would be the actual opcode for add immediate. That would be the immediate field. RN is register 10, and R9 is, or register 9 is RD. Instructions that don't explicitly specify that they are unsigned, they are signed. So this addition would be signed. And again, this is the binary patterns and hex. So in the immediate arithmetic instructions, the immediate field, remember, is 0 extended. So we're going to stop here, and then we'll do another example of a C expression when we come back on Thursday. And we see how we handle the extension, and when we have explicit unsigned or implicit signedness, and how we sort all that through the different instructions in the ISA. All right, so we'll stop here, and we'll take it from here on Thursday.